I'm Anil Kumar. Welcome to my series on rational functions. We'll try to understand how to sketch graph of rational functions. So I've taken up 7 examples here. We'll go through their graph one by one. We're going to look into key parameters like vertical asymptote, horizontal asymptote, oblique asymptote, holes, y-intercepts, x-intercepts, domain and range. Now these are very key parameters which basically define your graph. Now there are some other parameters like increasing interval. I should write increasing or decreasing interval. Discontinuities. And whenever we talk about rational functions, we talk about restrictions, right? Another thing which I think is very important is symmetry. A function could have even or odd symmetry, right? Now these are other parameters, but anyway, this will give you a good understanding of most of the terms on this page. Now we are not going to answer, but you have to think about these questions when we go through the solutions or the graph of our 7th set of simple examples, I should say. Once we are done with this video, you should be in a position to figure out which of these graphs is an even function, which of them is an odd function, which is always increasing, which of these function is not increasing nor decreasing, has no asymptotes, or do we have any rational function which crosses horizontal asymptote, right? So that will give you more information from what we talk about. So that is the kind of strategy with which you could watch this video, right? So let's take the graph, which is key idea here is to just sketch the graph. But while we are sketching the graph, I would like you to also look into these aspects. Okay, so I hope that makes sense. Now let's begin with the very first example, which is we need to sketch the graph of function y equals to x squared minus 9 divided by x minus 3. So let's rewrite this function in factored form. So I could write this as x plus 3 times x minus 3 divided by x minus 3. Now when you look at this function, let me ask you one thing. Does it have a vertical asymptote? Now some of you will just jump to the conclusion that the denominator is 0, therefore it has a vertical asymptote. However, now you see that x minus 3 is a factor which cancels. And therefore what really remains here is x plus 3. Of course, there is a restriction that x is not equal to 3. Now what does that mean? It simply means that we have a hole in this situation and the location of the hole is at x equals to 3. So this is a key feature of our graph. The type of discontinuity which we have here is not a vertical asymptote, is a hole, right? And what is the point at which we have this hole? Let's substitute the value 3 in our function, which is x plus 3. So if I write 3 plus 3, I get 6. And therefore, we can say that we have a hole at 3, 6. Perfect. Now it is important to note that there is no vertical asymptote. So I hope you clearly understand this part. There is no vertical asymptote. Now, do we have horizontal asymptote? Since the degree is higher of the numerator, we do not have horizontal asymptote. Now my question here is, do we have vertical asymptote? Oh no, oblique asymptote. Now the question is, do we have an oblique asymptote? Take your time to answer this question. Correct? Now let me find out x and y intercepts to sketch this particular graph. So to find the y-intercept, let's take y-intercept first. It is simple. What we have to do is we have to substitute x equals to 0, right? So at x equals to 0, y is equals to 0 minus 9 over 0 minus 3. So that gives you 3. So we do have y-intercept, and the location of y-intercept is 0, 3. Perfect. Now, do we have x-intercept? So for x-intercept, y should be equal to 0. That means the numerator should be 0. Perfect. So this gives you that the numerator, which is x squared minus 9, that should be 0. Correct? Now in our case, we simplified our function and we got this x plus 3 as our numerator. Right? So the whole thing is x plus 3. So therefore, we could substitute in this simplified expression where the restriction is that the function cannot be 3. Correct? So y is 0 means x plus 3 is equal to 0, and that gives you the point that x is equals to minus 3. Correct? So we get the y, sorry, which gives you the point that x, so the x-intercept, yes. So x-intercept is when y is 0, x plus 3 is 0, and that gives you that x is equals to minus 3, right? So this gives you that x is equals to minus 3. Therefore, x-intercept is at minus 3, 0. Perfect. So we have most of the important parameters which can help us sketch this particular graph. Now what you also notice here that, so I'm going to make very rough sketches here, okay, with critical parameters highlighted. That's the whole idea. Perfect. So what we get here is a straight line with a hole at 3, 6, right? So that is how it is. Y-intercept being 3, x-intercept being minus 3, correct? So a straight line like this could work. Now that point is a hole for us. Does make sense to you, right? So that is how we are going to sketch our line. This point right there is at 3, 6. And these intercepts are at 3 and minus 3. And that is our function y, x squared minus 9 divided by x minus 3. Now once you get your function, it's good practice to write domain and range. Perfect. You could have written right there that domain does not include 3. So we can write domain as x belongs to real numbers where x is not equal to 3. We have a hole there, and the range y is y belongs to real numbers where y is not equal to what? Y is not equal to 6. You see that part, right? So that is how we get our graph, and we kind of get all our understanding about the key parameters. Now, can you tell me whether this function has a horizontal asymptote or not? It does not. You can see that. But the question here was main, Do we have an oblique asymptote? Degree of numerator is 1 higher. The answer is no. We are not approaching any value. We are right there. You understand? So we are not approaching this line. We are on this line, and therefore it has no oblique asymptote. That's a very, very important thing to understand. And this function is always increasing, right? So I hope you got those answers. Let's move on and take the next example. Now let's take the second function, which is y equals to 2x minus 6 divided by x minus 3. Clearly, we do have a restriction, which is x cannot be equal to 3, right? So let's rewrite this function, which is y equals to 2x minus 6 divided by x minus 3. So we know that x is not equal to 3. Now what type of restriction we have? Does it lead to oblique asymptote, vertical asymptote, whole, or what, right? Let's try to figure this out. We could factor the numerator, 2 factored, we get x minus 3 in the numerator divided by x minus 3, and from here you could cancel and we just get a constant 2. Perfect, and we know x is not equal to 3. So what do you really notice here? That this particular rational function reduces to a constant value of 2, right? So if I have to sketch, then what do I get? Since there is a common factor, we have a common factor in numerator and denominator. That leads to whole, right? That leads to whole. So just as we had in the previous example, and the location of whole is at x equals to 3, which is a part of our discontinuity, right? But the y value is always 2. So this location of whole is x equals to 3, y equals to 2, or the coordinate point is 3, 2. Perfect. Now, do we have any asymptote in this particular case? Clearly, it's just a constant function. We have no asymptote in this particular case. Is that absolutely clear? So we could have rational functions without any asymptote. Perfect. So there is a hole at 3, 2. So let's say this is the function with a hole at 3, 2, and then it moves forward. And a horizontal line represents this particular function. X-intercept, we don't have any. We do have a y-intercept at 2. No oblique asymptote, no vertical asymptote, no horizontal asymptote. So you can now write all the characteristics, including domain and range, for this particular function. So let me write down at least the domain and range for you. It is, domain is x belongs to real numbers, where x is not equal to 3, and the range is what? What is the range in this case? Well, the range is just 2. So in the range, we have only 2. Do you see that? It's a constant function. Perfect. So here we have a very unique example of a rational function. So I might have taken just 7, but they will give you complete spectrum of rational function. That's the whole idea. For difficult questions, we have many other videos, but this video is mainly for concepts. Okay, now let's take the next one, which is y equals to x minus 2 over x squared minus 4. Let's rewrite. We need to factor the denominator, then see the result. X squared minus 4 could be written as x plus 2 times x minus 2. Now here again, we do have a factor common in numerator and denominator, and that leads to what? On a graph, you will see this as a whole, right? So that is kind of important to understand. But when we write restrictions, we have to include both the restrictions. So x cannot be equal to plus and minus 2. Now some students just forget about this after cancelling, which is a huge mistake. So in this particular case, we do have a hole, and the location of hole is at x equals to 2, the factor, right? So the x value is 2. When I substitute 2 here, I get 1 over 4. Do you see how easy it is to calculate? Perfect. So that becomes the whole. And for this particular function, we do have horizontal asymptote, since the degree of denominator is higher, right? So the other characteristics is that we have a horizontal asymptote, which is y equals to 0, correct? Now, after cancelling, we still have x plus 2. That means we do have a vertical asymptote, and the vertical asymptote is at x equals to minus 2. You can also find x and y intercepts now, correct? So let me use the space which I have right here to write x and y intercepts. To get y-intercept, we have to just write 0 for x and you get half, right? So y-intercept is at y equals to half, and x-intercept is when the numerator is 0. So what do you notice here? Do we have x-intercept? The numerator can be 0 at x equals to 2. However, x equals to 2 is a restriction, correct? So we do not have any x-intercept, so none. With this, let's sketch our graph. So we do have a horizontal asymptote, which is y equals to 0. That means the x-axis. So that is the horizontal asymptote. There, the curve is approaching 0 when x approaches infinity. That is the meaning of horizontal asymptote, right? So when we say horizontal asymptote, we mean what? We basically mean if x approaches infinity, y approaches a value L, or it could also mean when x approaches negative infinity, y approaches some value, let's say L. Now these values could be different. So you could have two asymptotes, horizontal asymptotes. Okay, these values could be different. It's kind of important to understand that part. Okay, now in this particular case, we know we have a vertical asymptote at minus 2. So let me sketch this vertical asymptote now. So first, you should sketch your asymptotes. That makes things simpler to understand. And now, let's look into the x and y intercepts. So the y-intercept is at half. Let's say this is half for us. That's the y-intercept. We have a whole, which is at 2, 1 over 4. So 2, 1 over 4 will be kind of here, somewhere very close. So since, let's say we move it like this. Perfect. If I have a value which is closer to, which is on the positive, see this is the vertical asymptote, let me write like this. This is the vertical asymptote x equals to minus 2. If I have a value which is slightly more than minus 2, I mean the right side, then what happens to this graph? Is it positive or negative? That is what we have to look into, right? So if I have a value which is, let's say, minus 1.9, so it will be positive. So when you approach from the left side, it is positive, correct? So we say behavior. So when x is approaching minus 2 from the right side, right? That is, you can substitute a value minus 1.9, for example. So in that case, this graph will be positive, so you are approaching like this. But when x is approaching minus 2 from the left, this is from left. That means you could put a value like minus 2.1. In that case, this becomes negative, so it approaches like this. You get an idea, right? So this helps you to sketch the graph. We have critical points, so we can, using these points, sketch our graph as this. Approaching 0. Perfect. Here again approaching 0. You could take few points to get accuracy in your curve. Perfect. However, I hope that makes sense. Now I'll leave the part of writing domain, range and all other things for you. Of course, the domain will not include these 2 points, x not equals to plus minus 2, and the range will not include the position of the whole, 1 over 4. Perfect. All others will be included in your domain and range. Correct? So this point here is the whole, which is at 2, 1 over 4. Right. So let me write this as 2. Then we do have a x-intercept and y-intercept, which is at half. So this is properly labeled to y equals to 0 is your horizontal asymptote. So I hope all the concepts are absolutely clear as far as sketching of this rational function is concerned. Now this is a very typical rational function graph which you normally see. The previous 2 examples were kind of exceptions to many rules. Let's move on and understand few other characteristics of rational functions. We need to graph and find characteristics of y equals to x squared minus 1 divided by x. Now in this particular case, degree of numerator is 1 higher, so you expect an oblique asymptote. So let's keep this in mind while working on this particular function. So we could rewrite this function y equals to x squared minus 1 over x as, let me rewrite as x squared over x minus 1 over x. Okay. So that really means I could write y equals to x minus 1 over x. Correct? Now the restriction is that x is not equal to 0 since the denominator cannot be 0. Perfect. Now, with this, what do you get? The function is x minus 1 over x. Then, if x is approaching a large value, let's say infinity, then 1 over x is approaching 0. So we are basically approaching, so y is approaching x. Do you understand? What I'm trying to say here is that in this particular case, if I sketch my graph, then I do have a line which we'll call as oblique asymptote, which is x. This is the line y equals to x. And when x is very large, that means we are going to this side. 1 over x is a small value, but it is negative, less than x. So we are approaching this line from this side. Do you understand this part? Perfect. So this is very important to understand. That gives you the behavior at the end. We also call this as end behavior. Sometimes you may have oblique asymptote when the degree is higher, and sometimes you may have horizontal asymptote if the degrees are same or the denominator degree is higher. Correct? Now let us also analyze what happens when x is approaching negative infinity. So negatively large number. So if I substitute minus 1000, this becomes positive, that the value of the function is more than the line. So you are again approaching this line, but in this way, above the line. You get an idea, correct? So that gives you behavior near the asymptote, oblique asymptote, right? How do you approach, how the graph approaches the asymptotes? Very critical. So what we did in this part here is we analyzed oblique asymptote. Okay, now sketch the other things, which are x and y intercepts. So from this function, we know that x cannot be equal to 0, right? X is not equal to 0. However, y could be 0, right? So y could be 0 for 2 values of x. So that gives us x-intercept. So that is at x equals to plus minus 1, correct? So those are two intercepts. And we do have a vertical asymptote, which is x equals to 0, of course. That is a restriction. So let me sketch the vertical asymptote, which is right there, the y-axis. We do have two x-intercepts, one at plus 1 or minus 1, one at plus 1. And we see that the graph is approaching the oblique asymptote. So with that in mind, we could actually sketch our function as kind of like this. Do you see that part? Here again we are approaching the asymptotes. There we are approaching the y-asymptote. So that is how the graph will look like. Right? So the curve should have been better. I should have drawn like this, kind of. Do you understand? So it has to be more curved, which I didn't really get since I wanted to go through minus 1. Okay. But I hope that makes sense. So that is how you need to sketch your function. So this is an example where we do have a vertical asymptote, an oblique asymptote, and what is the range? It is important to understand that domain has restrictions, however, range is what? Y belongs to real numbers. There is no restriction on the range in this particular case. Let's move on and take some more examples. This time we have our function, which is y equals to x over x squared minus 1. So let's rewrite this function as x over x plus 1 times x minus 1. Right. So from here we get vertical asymptotes, two of them. One is at x equals to minus 1, the other one is at x equals to plus 1. Since the degree of denominator is higher, we have a horizontal asymptote, which is y equals to 0. The x-intercept is when the numerator is 0, which is y equals to 0. The y-intercept is, y equals to 0 and x equals to 0, right? The y-intercept is also at the same point, correct? So you substitute 0 for x, and what you get is y equals to 0 in this particular case. Now, that should give you a good enough graph, correct? So let's sketch the graph now. We have two vertical asymptotes. One is at plus 1, the other one is at minus 1. We also have x and y intercept right at the origin. So the graph is crossing this origin. And horizontal asymptote, as you note, is the x-axis. So basically we are crossing the origin, correct? So this is a very interesting example. Minus 1 plus 1, 0. Now take some test points to really get some values. So what you should do here is, I will suggest take few points. So take some x values and calculate y values to get accuracy, right? So good points, we already know one point is 0, 0. Now you take a point as half, 0.5, correct? Somewhere. Minus half. Perfect. You will find that this graph has a symmetry. So when I write half and minus half, you will kind of get a symmetry here. Okay. Then you could take a point as 2 and let's say minus 2. Plug in these values, get these points here, and then sketch your graph. Perfect. So for the time being, I'm only sketching the graph for you. It will look like this. So what you notice is that it crosses the horizontal axis, right? If I take a positive value greater than 2, then this function is always positive. So I get it on the right side of the asymptote. If I take a value x which is negative more than minus 2, I mean left side of minus 1, in that case this portion is negative, so I get a graph like this. So if you have calculated these values, you are able to position those points, right? So I'm positioning these points only to tell you that it is symmetric. Now this graph is symmetric about the origin and it has odd symmetry. I'd like you to write domain and range. Of course, range has no restriction. Do you see that part? So that is how we get, graphs and we understand their characteristics. So let's move on and see other examples. Now here is another very interesting example. Y equals to 1 over x squared plus 1. Now here what you notice is that denominator is never 0. That means no vertical asymptote. Degree of denominator is higher. That means we have a horizontal asymptote which is y equals to 0, right? Since the degree is higher. So to sketch this graph, let me sketch some basic things, which is we have a horizontal asymptote. That is it. Now what else? Now there are a couple of ways to do it. We could use our knowledge about reciprocal function to sketch. That is to say, I could sketch x squared plus 1. I could g of x equals to x squared plus 1, which is a parabola. Let's kind of like this. And then what we really have here is the function f of x, which is 1 over g of x, which as you can see is 1 over x squared plus 1. So some of you could sketch it using this. Now not really that function, I'm so sorry. Move 1 unit up, I'm sorry. So parabola moved 1 unit up, so this is at 1. So the reciprocal of this will be what? Clearly 1 reciprocal is 1, and as you move higher, for these limits, reciprocal infinity is 0. The graph is always positive. Do you see that? So that is your function y equals to 1 over x squared plus 1. To get some accuracy, you take some points, right? So you could calculate this value for, like, let's say, so we could have some points as 0. If I put here, I get 1, correct? If I take x as 1, I get a value which is half. If I take minus 1, I get again the same value, which is half, right? So you find that symmetric about y-axis, correct? So that implies from the graph also we have a function which has even symmetry. So these are the major characteristics. It does not have any x-intercept. The y-intercept is at 1. It has a local maximum, and therefore, what is the range of this function? So we know this, that the domain of this function is x belongs to real numbers, no restriction. However, range is that y belongs to real numbers, where y is greater than 0 but less than equal to 1. This is very typical of this graph. So there are two major characteristics which you see in this example. One is that it's an even function. The other one, that range has no restrictions. I mean, the domain has no restrictions and range has restrictions, correct? So domain is not restricted. Perfect. Now let's take the example where we have restrictions in domain and range. I hope by now you have learned many techniques. You can actually pause the video, answer this question, and then look into my suggestions. We need to sketch the graph of y equals to x squared plus x minus 6 divided by 3x squared minus 12. First step is to factor. Product of minus 6, sum of 1. So we get x plus 3 times x minus 2. In the denominator, I could factor 3. So we get x squared minus 4. Now this can be further factored. So let me write this function as y equals to, in the numerator, I have x plus 3 times x minus 2. And in the denominator, I have 3 times x plus 2 times x minus 2. So you can cancel x minus 2. So this is a very interesting example where you have a lot of things to look for. So since that cancels, we have a whole. And the x value is 2. When I substitute 2 here, what do I get? 2 plus 3 is 5 divided by, if I substitute 2 here, 4 times 3 is 12. So that's the location of the whole. Now, we have a vertical asymptote. At x equals to minus 2, we have a horizontal asymptote. Since the degrees are same, the horizontal asymptote is y equals to 1 over 3. So how do you find horizontal asymptote? We compare these coefficients. I'd like you to watch some videos on this, how we find horizontal asymptotes. So when the degrees of numerator and denominators are same, it's the ratio of leading coefficients. Let me write down. Ratio of leading coefficient. If degree of numerator and denominator is equal. So it is 2 here for both numerator and denominator. So it is, as you can see, 1 over 3. Correct? So with that, let's sketch, make a rough sketch. So we have a horizontal asymptote. Let's say this is 1 over 3. Vertical asymptote at minus 2. This is minus 2. Okay. So this is, we have x equals to minus 2. So this point here is minus 2. This is 1 over 3. Okay. Now again, let's find x and y intercepts. Let me use this space here to find intercepts. So x-intercept. X-intercept means touching or crossing the x-axis where y has to be 0. That means numerator is 0. And in our case, numerator is 0 at minus 3. Right? So if I write minus 3, then we do get numerator 0. That means it crosses at this point, which is minus 3. X equals to minus 3. And y-intercept is when x is 0. So if I substitute 0 here, I get minus 6 over minus 12, which is plus half, right? So we could have these points here. The y-intercept is, let's say here. And the whole is at 2, 5 over 12. So somewhere here, above the line. Okay. So that should help us to sketch the graph. We do have a vertical asymptote and the whole. You could take some other points, however, this is sufficient. So we have a graph which is kind of like this. So you're approaching the horizontal asymptote from above. That's the whole, right? So that's the whole. So let me sketch this. Do you understand? And on this side, we are approaching 1 over 3, going through the x-intercept, approaching the negative infinity mark along the vertical axis, right? Do you see that? So that is how you could sketch this particular graph. So I'd like you to write other characteristics of this particular graph from what we have done. So that brings us to the end of this video. I hope you got some exposure about graphing rational functions. These 7 examples which we took help us to understand many different concepts. Now to review, I have an exercise for you. Here are these 7 functions which we considered. Y equals to x squared minus 9 over x minus 3. Y equals to x minus 2 over x squared minus 4. Y equals to x over x squared minus 1. Y equals to x squared minus 1 over x. Then we have y equals to 2x minus 6 over x minus 3. Y equals to 1 over x squared plus 1. And y equals to x squared plus x minus 6 over 3x squared minus 12. I would like you to sketch their graph and write down their characteristics. So your question now is sketch graph. And write characteristics. Perfect. Take your time, copy these questions. Let me show you all these solutions once again. So we'll just sketch their graphs right here. I'd like you to also do this exercise simultaneously. That will reinforce our learning about rational functions, which we just did in this particular video, right? Okay. In the very first one, when you factor, one of the factors cancel away, which leads to a whole. So this is not a vertical asymptote, but straight line, which was a graph kind of like this with a hole here, right? So that is the graph of the function. The second one here, which has a denominator which can be factored, x plus 2 times x minus 1. One of them leads to a whole, the other one to a vertical asymptote. Whole is at 2, vertical asymptote is at minus 2. So let me sketch the vertical asymptote here and the whole at 2. So it's kind of like this. Horizontal asymptote, since the degree of denominator is higher, is y equals to 0. Perfect. Now this graph here is symmetric about the origin. It has 2 vertical asymptotes at plus minus 1. X-intercept right in the center and looks like this. Horizontal asymptote is y equals to 0. Clear? The next graph here is degree of numerator is 1 higher. It has an oblique asymptote, right? So let me sketch the oblique asymptote, and it approaches oblique asymptote from below on the right side, and this is the vertical asymptote. Perfect. So it will not cross the vertical asymptote, so it's kind of like this. These 2 points being plus minus 1. This was interesting. When you factor 2, you get x minus 3. It cancels, leads to a whole. So in this particular case, you are left with 2. So it's 2 with a whole. It's a constant function. So this graph doesn't increase or decrease. Here, denominator is never 0. So the domain is all real numbers. And if you sketch, you get something like this. Perfect. The last function here, when you factor out, you do get a common factor which leads to a whole. And then we also have a vertical asymptote. So we found that this graph was kind of like this. One over 3 is your horizontal asymptote. So let me sketch the horizontal asymptote here, which is not the y-axis. It is y equals to 1 over 3, which is the ratio of this, right? Leading coefficients. Now with that, we come to an end of our video. I hope you have learned a lot from here, and you have all the answers for what we began with. Now here is another question for you which you can think about. We'll talk about this function in the next video. Thanks for your patience and your time. I hope it was a learning experience. If you feel good about it, you can share with your friends, and also I'll be happy if you could subscribe to my channel and get more of the same. Thanks a lot once again.